So, we spend a ton of time talking about how to amplify signals, right? How to make them bigger, stronger, clearer. But that kind of brings up a huge question. Where do these signals even come from in the first place? How does a circuit literally conjure a wave out of thin air using nothing more than a steady DC power supply? Well, that's exactly what we're going to break down. First, we'll get into the secret recipe for creating a signal from, well, nothing. Then, we'll look at how circuits cook up two totally different flavors: the smooth, rolling waves of the analog world and the sharp, precise pulses of the digital one. And to top it all off, we're going to meet a legendary little chip that can do it all. So, let's dive in. All right, first up, the magic trick itself. How do you take a totally flat, boring DC voltage and convince it to start wiggling, to start oscillating? Well, the key is to embrace something we usually try to stamp out in amplifier design: positive feedback. I mean, this really is the fundamental challenge, isn't it? You've got your power source, just a steady stream of energy. The whole goal is to build a circuit that takes that stability and uses it to spontaneously generate a rhythm, a consistent, repeating waveform that becomes the very heartbeat of whatever device it's in. And here it is. This is the recipe, the two golden rules for making it happen. First, the signal has to loop back on itself perfectly in phase. That's the 0-degree phase shift part. It has to reinforce itself, not fight against itself. And second, the loop gain has to be exactly 1. Not 0.99, not 1.01, exactly 1. Any less, and the wave just fizzles out and dies. Any more, and it spirals out of control into a distorted mess. So how on earth do you hit a gain of exactly 1? That's like balancing a pin on its head. Well, here's the clever part. In the real world, you kind of cheat. You actually start with a gain that's just a little over 1. That gets the oscillation started and lets it grow. Then, just as it's getting big enough, a little limiter circuit kicks in and automatically pulls the gain back down, locking it in right at 1. It's a beautiful, self-correcting system for a perfectly stable signal. Okay, so now that we've got the theory down, let's see how this plays out in actual circuits. We'll start with the ones that generate those beautiful, smooth sine waves. You know, the foundational signals for everything from your favorite song to the radio waves that might be carrying this to you right now. And really, it all comes down to using the right tool for the right job. You see here, for lower audio range frequencies, simple resistors and capacitors in what's called a Wien-bridge oscillator do the trick just fine. But to get up into the really high radio frequencies, or RF, you need the heavy hitters, inductors and capacitors, like in a Colpitts oscillator. And for just rock-solid, ridiculously precise timing, like the clock inside your computer, nothing, and I mean nothing, beats the weird magic of a piezoelectric quartz crystal. And get this for a cool piece of history. That first one we mentioned, the Wien-bridge oscillator, it's not just some diagram in a textbook. It was the very first product sold by two guys named Bill Hewlett and Dave Packard. They built it in a garage in Palo Alto. And that humble little audio oscillator, well, that was the product that launched HP, a true Silicon Valley legend. All right, so we've covered the smooth, flowing world of analog waves. Now let's slam on the brakes and jump into the digital world, the world of sharp edges and absolute states. It's either on or it's off. And this is the domain of a family of circuits called multivibrators. They were born to do one thing: flip back and forth. The secret to telling these guys apart is their stability, or you could say how comfortable they are. A bistable circuit is totally happy sitting in one of two states, which, you guessed it, makes it a perfect little memory switch. Then you have the astable circuit. It's never happy. It has 0 stable states, so it just restlessly flips back and forth, forever. And finally, there's the monostable. It has one state it loves. You can trigger it, push it over, but it'll always pop right back after a specific amount of time. So what do we get from these different personalities? The bistable, with its 2 states, becomes a memory element, a flip-flop. The restless astable circuit becomes our digital clock, providing that steady beat for every computer out there. And the one-shot monostable becomes a super precise timer. Oh, and here's a cool little trick. If you take that sharp square wave from an astable and integrate it, you can smooth out the edges and create a perfect triangular wave. Okay, so all of this theory about multivibrators, it all leads us to one of the most iconic, most beloved components in all of electronics. I want you to imagine taking all these fundamental building blocks and packing them into a single, dirt-cheap, and incredibly versatile little chip. Well, that chip exists, and it's the legendary 555 timer. And look, the 555 is famous for a reason. It's a pre-packaged powerhouse. Inside this tiny little chip, you've got all the essentials: the comparators, the flip-flop, the whole shebang, All you have to do is hook up a couple of resistors and a capacitor on the outside, and boom, you can make it an astable oscillator or a monostable timer. It really is the Swiss Army knife of timing circuits. So, think about this for a second. Right now, as you're watching this, from the quartz crystal oscillator ticking away billions of times a second inside your phone's processor to the LC oscillator crafting the Wi-Fi signal that's delivering this content, which of these tiny engines is powering your world? They're the invisible, unsung heartbeats of our entire modern age. And that's our look at the tiny engines that make the electronics world go round. Now, if this explainer helped you get a handle on the heartbeat of electronics, then there are 3 super quick things you can do to help us out. First, just hit that like button. It really does tell the algorithm that this was useful stuff. Second, make sure you subscribe so you don't miss our next deep dive. And finally, ring that little notification bell. That way, you'll be the first to know when the next one drops. Thanks for watching, and we'll see you in the next one.